Hi, ma'am.
Yes,
Yeah.
yes.
It's just a small request to kindly solve the week 4 assignment, ma'am.
Week
Week 4
four
assignment.
assignment.
Uh,
Okay, so week four has questions related to D StatCom, right?
yes, ma'am.
Yeah, yeah. So today we are going to solve these questions.
Yes. Okay. So, actually, it is difficult to find the solutions. Okay. So that's why. Mm.
Okay, okay. We'll be solving similar questions today. You can have an idea from there.
Okay, ma'am. Yeah.
And I will say you also had some questions, right?
Hello, Angel ma'am.
Yes, sir.
My doubt is in assignment 3, one problem is given on series compensation, ma'am.
Okay.
In that, the question is calculate the voltage across the load without and with compensation. So we get two answers. One is the voltage across the load without compensation, and one with compensation. But in answer you have to write only one.
Yes,
But
you asked the same question last time as well, right?
yeah, you suggested me to write the with compensation voltage across the load.
Yes, yes. And I also asked you to raise this query on the discussion forum. Did you get any response there?
Yeah, but unfortunately, my answer got wrong, ma'am.
Okay, no, so they will, didn't they award marks to all there?
No, it is showing your answer is wrong.
Okay, so when you told them that there was only one box and two questions, then what did they respond with?
Yeah, yeah.
Madam, good evening, madam.
Good evening, sir.
Madam, I kept that question in discuss forum, madam. They will reply, madam, like you have to write without compensation. You have to write the voltage across the source without compensation. They will be giving the answer like that, madam.
Oh, without compensation you have to write. But they have asked for both, right? So it is
That is the
confusing.
But I
uh,
calculate without
means
compensation.
in discuss forum they are giving answer, madam. In discuss forum, I ask a question in the tab.
Okay,
I
okay.
post a question. Then they replied that giving a replied that you have to give the answer
Without
without
compensation.
compensation.
Okay.
Okay,
Because
okay,
why I
okay.
asked you, ma'am? Because if I got the same question in the end exam, but I should know which answer I have to write. That's why I asked you.
Yes, yes, that is why, as Venkat sir mentioned, right, that in discussion, whenever there is some kind of query, on day one when you get the assignment, just go through the questions one. If there is any such query, then just put the query that day itself, because they also need some time to respond back, right? So that by the time you are actually submitting the assignment, all your queries will be solved beforehand.
Otherwise, they should provide a special box in that you have to mention both answers. That will be easy for us, ma'am. Because I have done the question, I have solved the question, I know the answers, but unfortunately, I have written with compensation. But unlucky, my answer got wrong.
Okay, okay. From next time, you please check the discussion forum before submitting the assignments, because, like as Venkat sir mentioned, right, the query was already discussed on the forum. So if you would have seen there, then you would have got the answer right.
Oh, okay.
Okay. Okay, guys. So shall we start today's session? Anybody has any other doubts?
Madam, in assignment 3, question number 8 and 9, we will ask the Farad and Henry, madam. But we will consider in microfarad and millihenry. So,
Okay, they mentioned farads and henries, and they considered the answer in millihenry and microfarad. Is
microfarad and
that what you are
millihenry.
saying?
No,
Actually, we will ask the Farad and Henry. So,
Yes,
we will
yes, yes.
consider the answers in microfarad and millihenry.
Okay,
no,
okay,
we
okay,
have to
That's why
okay.
my answer is wrong.
we have to correct it in, ma'am. Actually, it is asked in calculate in millihenries and Faradays means you have to correct that, not B LC. It is a CLC or LLC. That
No, so in that case, have you complained about this? That the answer was in asked in another unit and the answer is being given in another unit. Did you complain this on the discussion forum?
And in feedback form, I will comment this. I will comment, madam, in assignment.
Okay, but for assignment related queries, do comment on discussion forums. So in case you are commenting right now on discuss, because feedback form might not, I don't know if the TAs get the access to feedback form. So you should put this query on the discussion forum. And since they have asked different units and they have given answers in different units, the marks to all should be awarded most probably. That should happen.
Okay, okay, madam.
So you should put up this kind of queries there.
Okay.
Because the problems are prepared by somebody else, solutions are prepared by somebody else, then they are submitted by somebody else. So in these process lot of problems happen. So if you point it out to them and they find it reasonable, they will definitely give the marks. You should not worry about it,
Okay,
but
okay,
you
madam.
just bring it to their notice. Okay.
Okay, okay.
Okay guys, then shall we start today's session then?
Okay, madam.
Yes sir. Okay. Okay, so I'll start today's session then. Okay, guys, so as most of you know that I am Anshul Singh Thakur. I am a PhD student at ICER department, that is Interdisciplinary Center for Energy Research at IIC Bangalore. And I'll be your TA for this course. So I'll be single-handedly taking the TA for this course, which is Power Quality, offered by Professor Bhim Singh sir on NPTEL platform. So today this is the week. I request all of you to please mute yourself. I think some of you have mics on. Okay. So today is our third tutorial session, and so we'll be in past few lectures we have discussed about power quality, the need for power quality, and what are the power quality measurement instruments that are available in the market, and then we looked up at passive compensation techniques. So passive compensation techniques is the most basic form of compensation that is available out there. So after that, from today, we will start active shunt compensation. So in passive shunt compensation, what happened was I had a system. Suppose this was my system. This is a three-wire system. So I was putting some fixed value elements. Let me say I am connecting a star compensator. So these elements that I was putting had fixed values. Their values once put cannot be changed. So this kind of compensator was called passive compensator. But now we know that the electrical load, suppose this is our source and this is our load. Now, since we know that the nature of the electrical load changes from time to time, we know that this load is going to vary. Suppose at 1 p.m. we have very less lighting loads. At 1 a.m. at night, we'll have a lot of lighting loads because all of us will be sleeping in our homes. We'll be turning on the ACs. So from time to time, from every minute, there is a change in the nature of load. So when we are putting this fixed kind of compensation, shouldn't it will not be exactly able to compensate this load which is varying in nature. So since this load is varying in nature, an idea came up where we thought of making this compensation also varying in nature, depending on the nature of load. So in some places, so the reason so the only advantage of passive compensation is it's cheaper. So we just have to buy a one time investment and just put these compensators over there, and most of the time they will be able to meet the requirement. So in most of the factories they put passive compensators because the factory load is almost constant most of the time. But when we talk about the load of apartment buildings or any other commercial buildings or educational centers, then this load keeps on varying. So with the advent of, we had also discussed, right, the recent kind of loads which are coming into market. which are having power electronic front ends, and then there are electric vehicles. And suppose I am charging my electric vehicle right now, so my electrical load consumption will be very high. Later on, if I am removing it my consumption will reduce. So because of the dynamic nature of our loads, due to the presence of renewable sources of energy, electric vehicles, power electronic base loads, all these things, because of the nature of varying load, we thought of varying the compensation that we are putting there. So this kind of compensation that is varied with time is called active compensation. And the one which is fixed is called passive compensation. Okay, so depending on the kind of load and the nature of variation of load, we select the kind of compensation. But definitely when we talk about active compensation, now active compensation compensators are made up of switches. So there will be in active compensators what happens is there are switches and passive elements. So switches along with passive elements form active compensators. So when we are talking about active compensators, because of the presence of switches and its dynamic nature, and since we are putting switches, we will have to give pulses to these switches. There will be a lot of additional circuits required. So because of those things, what is happening is the price of active compensators is high. And that is the reason that although active compensation is a much more precise compensation for any kind of load, still we are using passive compensation only because of the cost problem. Okay, so now we have discussed about the need of active compensation compared to passive, which we have discussed so far. Now let us start with active compensation. So I'll briefly go to the revision of what Sir has gone through in his lectures. So we know that there are two kinds of power quality problems, voltage and current, and both of them have for power quality problems there is sag, swell, voltage imbalance, flicker, transients, etc. And for current power quality problems, we have power factor, voltage regulation, unbalanced current, excessive neutral current harmonics, etc. So, till now we have looked at passive compensators. Then, when we talk about active compensators, there are a lot of examples available. There are D-stack pumps, there are dynamic voltage restorers, there are UPQCs, which are unified power quality conditioners. So D-stack pump is a shunt connected compensator. DVRs are series connected compensators, and UPQC is a hybrid compensator which has both shunt and series components. So we will start with these StatCom, and then we will move on to other types of compensators. Okay. So since we know that these StatCom is connected in shunt with our system, therefore we know that when we are connecting any device in shunt, we are targeting current power quality problems. So we will be targeting current power quality problems using the D-StatCom. So in D-StatCom, the latest technology is being able to compensate the reactive power. It is able to balance the load which is connected to the output terminals. It is able to make the neutral current zero. It is also able to compensate for the harmonic current. So all these together, all these functions can be performed together using the D-StatCom. It can regulate voltage, it can suppress the voltage flicker, it can improve the voltage balance. All these tasks can be performed by D-StatCom. So classically, we already know that we used to classical technology for power compensation. We already know we have discussed passive compensators, and then initially before D-StatCom, there are few traditional active compensators which are called as thyristor controlled reactor and thyristor switched capacitor. So instead of putting a capacitor as a fixed compensator across a load, initially a thyristor switch was put. This is called thyristor switched capacitor. This is capacitor C1, this is capacitor C2, and this is my load. So this C1 and C2 will be of different values, and what we used to do is, depending on what is the need at the particular moment, we used to turn on these thyristors. So this was a very basic kind of active shunt compensation. But as new technology of devices came, all of us have seen the evolution of power electronic devices from thyristors to signal level IGBTs and BJTs, and MOSFET to power level devices. So all of this evolution we have seen. So with the advent of IGBTs, which is having the characteristics of both BJT and MOSFET, we started replacing IGBTs with thyristors as they were much more apt for the application and they were much more helpful compared to thyristors and they were very cost effective. So we started replacing with IGBTs. So nowadays the kind of shunt compensators that are being used are made up of IGBTs instead of thyristors. So these thyristor controlled reactor and thyristor switched capacitor, all these elements are not used that much nowadays. So, so the development of these STATCOM, there are varying configurations available. By configurations, it means is topologies like physical connection. It might be a 3-wire compensator or a 2-wire or a 4-wire compensator. And then there are advanced control strategies involved. So when you talk about DStatCom, there are two elements of a DStatCom. One is the hardware or the physical thing that you put, and another is the software that is written inside a microcontroller or a DSP board, which is present inside the DStatCom. So any kind of physical hardware, most power electronic hardware have both components, hardware body as well as software. So inside the software or the DSP, which inside the DSP board or any other control board that is present inside the DSP platform, we write codes in order to control the working of the DSP platform. So there we can have lot of control strategies. There are n number of control strategies which are available in literature nowadays. Literally on almost every month basis, a lot of control strategies come up and they're still coming up. So that is one area of growth. With the same topology, a lot of software control algorithms are being tested. So then with the and then devices, what kind of devices are you going to use? As we mentioned that active compensators have switches inside them. Right, there is a switch. Now which kind of switch are you going to use? Are you going to use a BJT or an IGBT or a MOSFET? So that the nature of the device that you are using. Then improve sensor technology. So there are a lot of so while in these STATCOMs, you will since you are doing a dynamic thing, right? Dynamic thing means on the spot. So when I am doing a dynamic thing, I'll have to sense the load, instantaneous values of the load current, the point of common coupling voltages. I have to find all these values. So in order to sense all these parameters, I will be using sensors. Now, sensors, if you search, sensors are available in lots of technologies. Isolated sensors, non-isolated sensors, Hall effect beat sensors, then simple non-intrusive sensors. Lot of sensors are available. So depending on your application and the accuracy that you want and the sensitivity that you want and the bandwidth you want, all these parameters, you choose a sensor that is used for making a DStatCom. And at the end, the brain of the DStatCom, which I mentioned, that the microcontroller or the DSP board. You program these DSP board or microcontrollers in order to execute any different kind of algorithms. Okay. So this is a few hardwares that Sir has shown. So just so that you won't be accessing the hardware while attending this course. But when you have a look at these kind of things, sometimes whenever you get to see a DStatCom, you will be able to relate to it. Okay. So these are D space boards. So nowadays what happens is you can directly do a simulation on MATLAB or Simulink, and then you can MATLAB will directly generate a program which can be fed through your hardware using DSpace. You won't have to write the code. So DSpace helps you with that. It skips the coding step. So this is how a DSP board looks like. The DSP chip is very small here, but the rest of the circuits are for programming this chip and the peripherals. So this together with these board forms the DSP control board. And a voltage source converter looks something like this. So these are the switches. And then the green PCBs which you can see behind them are the gate driver boards for these switches. And this is a fan for cooling these switches because thermal management is a very important part of any power electronic circuit. Okay, so these are the things that are happening. This is how a DStatCom somehow looks like. Then there are a lot of basis of classification of a DStatCom on the basis of the type of converter that you are using, whether you are using a voltage source converter or current source converter. Then on the basis of the topology, whether you are using a transformer based or without transformer, or and then on the basis of number of phases, whether you have a two-wire system or a three-wire or a four-wire system. So these are few of the classifications. Okay. Now let us go into details of the converter type classification. So your compensator could be current fed type or it could be voltage fed type. Okay. Now, when between the two, you could either use a current source converter or a voltage source converter. And the reason why voltage source converters are much more popular and used compared to current source converter is that because when you say word current source converter means it will be acting as a current source and it will be changing the direction of voltage in order to change the power direction. What I mean is, when you say that this is a current source, that means current will be in one direction and I will be changing the direction of voltage in order to power is a product of voltage and current. So if my current direction is fixed, then I will have to change the direction of voltage so that I can change the direction of power flow. So all the power electronics is about power flow, right? I am using these power, in the word power electronics itself has a word power. So I have some source, I have some load, and I need to put a power electronic converter to either pump the power from the source to load or from the load back to the source. If my load is a PV cell, then I will be pumping the power back to the source. And if my load is a motor, then I will be taking the power from the source. So depending on what kind of load I am connecting, I am doing bidirectional power, right? So in order to change the direction of power, I will have to change the direction of voltage in current source converter. Now, when I am saying the direction of voltage has to be changed, then I will have to give the negative voltage blocking capability to the rest of the switches. And these kind of switches are still not that cost effective and cheap. So that is the reason that because of the easy availability of switches and easy control, these kind of switches are easily available, which have the capability of a bidirectional current carrying capability instead of bidirectional voltage carrying capability. That is the most important reason why current source converters are not that much popular than voltage source converters. Voltage source converters are used in almost every other power electronic application. Okay, they are cheaper, they are lightweight, they are cost effective. These voltage. Another reason is in current source converter you have an inductor at the DC side, which is very bulky in nature. Whereas in the DC STATCOM, you have an electrolytic capacitor, which are cheaper and lightweight compared to the reactor that you're putting in current source converter. So that is also one of the reasons. And also the losses in voltage source converters are less compared to losses in voltage source converters are less when compared to current source converter, because if you can see in this combination, at the time either the switch will conduct or the diode will conduct. But in this case, if you see, at both the times, both of them will conduct together, the diode and the switch. So the losses will be almost two times compared to this one, because here at a time only one will be conducting, here at a time both will be conducting. So these are few of the reasons why voltage source converter is being used. And in our course, we are going to use voltage source converters. We'll be looking at the design and analysis and everything for voltage source converters, not current source converters. Okay. Now when we talk about supply system based classification, there are two wire, three wires and four wire systems. So again, you could either make it using a current source converter or a voltage source converter. Again, for the sake of this course, we'll be focusing only on voltage source converters. Then there are three wire STATCOMs. So these STATCOMs could be made in the could be of non-isolated type or isolated type. When we talk about non-isolated means there will be no transformer, there will be no isolation present. Okay, so it could be for three wire, it could be a 3-leg converter or a 3-leg with split capacitor. So we will be seeing all these configurations. So when we talk about 3-leg converter, there will be 3 legs. So this is a leg with 2 switches. Okay. So 3-leg converter is as shown here. So there are 3 legs present here. And then on the DC side, so this is the AC side and this is the DC side. Then on the DC side, there is an electrolytic capacitor present. which is used to eliminate the voltage ripple and then there is the ripple filter, which is used to eliminate the voltage ripple generated at the point of common coupling. So this is our source. This is the source impedances. These are not externally put; they are present in order to replicate the model of an actual distribution system. Because in distribution system, the source is not near to my house; it is very far from my house. So when this source is traveling, putting current from my house to my house from the generating station, then some impedance will come in between. So that is this. This is that impedance. Now this is my shunt compensator, which is connected in parallel to the grid using interface inductors. And then these are ripple filters. And the purpose of this ripple filter is to absorb the harmonic part of the voltages. Why? Because at these points, if you see that this point is a switched point. Since I will be turning on and off these switches, the voltage at this blue node will be switched voltages, will be pulse width modulated voltages. So because of the nature of this kind of voltage, what is happening is a lot of harmonics occur at this point of common coupling. And as a result of that, we are putting this external filter to suppress that harmonic voltage.
Hello, madam.
Oh, yes.
I putting two IGBTs, madam. Why, madam? You see, one is not sufficient, madam, for this.
So you are putting so in power electronics, what happens is this is a basic circuit. Okay?
Increasing rating for
No, so if you see
enhance the rating purpose, madam.
no. See, if you look at this point, since this I am talking about AC system, right? So at point of common coupling, I want to generate AC voltage, right? Which will be both positive and negative. Okay. So if VP is my if I connect only one switch S1, then what will happen is and I am connecting this to VCC and if I am connecting this to minus VCC, then at VP when S1 is on, then voltage is equals to VCC. And when S2 is on, at a time only one will be on. S1 is on, that means S2 is off. And when S2 is on, S1 will be off. This will be minus VCC. So you need these two switches in order to obtain both positive and negative voltages. Because if you will put only one, like if you have seen buck converters, right, DC to DC. So when you are doing DC to DC converters, one switch is sufficient. In all the converters, buck boost, and buck boost, all three types of converter, only one switch is used because you are operating between 0 and VCC. But here we need negative voltages also. So because of that, we are needing two switches. Because here,
Madam, here you have to converting load side. You are getting the AC, madam. After ripple filters, outside output of the filters, it is AC or DC, madam.
output of filters, yes, this point is point of common coupling voltage, right? This is 230 volt AC. And here we are generating switched voltages. What we are actually doing using this compensator is, so if you look at a big picture, this is my source, this is my load, and this is my compensator, a shunt compensator. Okay. Then what is happening here? Initially, when shunt compensator is not connected, then when there is no connection here, okay, let me say that this is not connected. Then suppose my load is drawing non-linear current, okay, then all that non-linear current has to be supplied by my source, right? All the non-linear, all the bad current and the good current, everything has to be supplied by my source. Now, when I am connecting this compensator, I program this compensator in such a way this load current initially had both bad part plus good part. Okay. So when this compensator was not connected, then source was supplying both bad and good part. Now when I am connecting the compensator and I am programming this compensator in such a way that it supplies the bad part to the load. Then using the KCL, what will be the supply current? The supply current will come out to be I good. That means the supply or the source has to supply only the good part of the current because the compensator is already giving the bad part, right?
Okay.
So
That it is compensation means it is converter, madam. I'm not
yes,
clear.
yes.
Compensation.
So what now what happens is now I know that I need to make a current controlled compensator that will supply the bad part of the current. So when I am talking about current control, so this is the compensator current of phase A. So that means I have to control ICA in such a way that it supplies the bad part of the load. Now, here this is a voltage source converter, right? That means it has control over voltage. So at this point A, what is happening is I am controlling the voltage at this point A so that the current in this branch can be changed. Because here we peak almost, we know that this point of common coupling is fixed. Okay, so there is this node B, then there is this node A. We know that at node B the voltage is almost same. We want it to be same, right? At 230 volt, 230 volt RMS. We know that the voltage is same at node B. Now when I change the voltage at node A, my current ICA value changes, and this is how I am controlling. So what I do is, from the load, from the nature of load, I identify what is the bad part of the load current, and then I make my compensator to give this bad part of the current, so that the source only has to give the good part. That means I will first monitor what kind of load is present. I will find out the bad part of the current, and then I will make my compensator to supply that bad part, so that the source has to supply only the good part. And since we are using voltage source converters, therefore using voltage source converter, we will be modulating the voltage at this point A, so that we can, in such a way that we can control ICA.
Okay, madam.
Okay.
Means my final doubt, madam, it will not convert to AC DC, madam. Conversion means voltage source
Yeah,
converters
so
means
you
it
can
will
call
be
it an
convert.
inverter. So this is DC and this is AC, right? So since you want to regulate this voltage as AC, since your grid is AC, so the voltage at node A will also be switched voltage. It will be AC. It will have both polarities, positive as well as negative. Whereas this side, this capacitor side will be DC and this will be AC. So this same topology you can use for an inverter. The only change between an inverter and a compensator is the control algorithm that is present inside the DSP or the controller of these converters. Because the same, like physically, if you see, all will be same. All will be made up of three legs. All will have an electrolytic capacitor. The only difference is how are we turning the switch on and off, and when are we turning it on. Okay. So if you look at DC choppers, then one H bridge DC chopper can be used as a buck converter. It can be used in all four quadrants. So you can have a look at it. So it's not, the physical body is almost the same. The only change is when I am turning. So by having different switching arrangements of these switches, I can obtain different kind of functions from the same converter. So it depends on what target I have. Okay. So you can call it an inverter. But the
Okay,
control,
madam. I understand, madam.
but the control algorithm will be different from that of an inverter. So then there is this 3-wire D STATCOMs with midpoint capacitors. So here at this point, so we needed connections to the three phases, phase A, B, and C. So we are using two legs here, and the third leg is connected at the midpoint of the capacitors. But the problem in this is, since the capacitors are carrying a phase current, the rating of the capacitors will increase, and also we have to maintain the unbalance of the capacitors. We'll have to maintain the voltage at these capacitors to VDC by 2 all the time. So this is different. So this is difficult to do. That is why what we do is we that is this is not a very popular topology that we use. Then there is, you can make the same system using 3 single phase voltage source converters, and you could use different combinations of transformers. Okay, so the most popular one in this is in 3-phase 3-wire is 3-leg converter, and in 3-phase 4-wire is 4-leg converter. So 3-phase 4-wire has more options. So you have already seen, right? Both non-isolated and isolated. You have, like, depending on application again, like you can use the transformer that you want. If you are using at a very high voltage and you need isolation, then only we go for transformer. Otherwise, in most of the medium power level, medium transmission level, whenever we talk about medium distribution level voltages between 230 to 400 volts, mostly the converters that are being available are non-isolated ones. And in non-isolated ones, 4-leg voltage source converter is the most popular one. Okay, so this is a 4-leg. So again, we have discussed what a leg means. So it will be similar to a 3-leg, only one additional leg will be added. And to the 4th leg, we will connect the neutral point. Then there is a similar system. So then there are other additional configurations that I think I all have already seen. Let us delve into the principle of operation, because you might have had some doubts there. So as I mentioned, that D statcom supplies the bad part of the current, bad part of the load current. Okay, so this is the schematic of the D statcom that the sir has in his lab. So it's a lot of equipment. So a non-linear rectifiers are put, inductive loads are being put. Then these are ripple RC filters. Then these are interface inductors. Then as I mentioned that in order, since we want to know what is the load right now, then only I can say what is the bad part of the load, right? So first of all, I like to sense the voltage at the point of common coupling and the load current. So I need sensor boards. So these are sensor boards. Then we need one DSP board in order to program. Then we need digital storage oscilloscope to take the waveforms. Then we have resistive loads. This is a very complicated system and all, but when you go block by block, then you will be easily able to understand it. So this is a voltage sensor PCB and the current sensor PCB that Sir has discussed, but I skipped these circuits because I don't think any of you will be interested in that. If you are interested, then you can let me know. We can have a discussion of these circuits as well. Okay. So let us discuss the design of these statcom. That if I am going to design this, what will be the value of the capacitor that I use? What will be the value of interface inductors and all these parameters? Okay. So now what is the role of this DC link that is present? So what happens is when we turn on these switches, the DC link, the current flows from the compensator to the point of common coupling. I hope all of you remember point of common coupling, right? So the point where we are connecting the compensator to our source load system, that point is called point of common coupling. So when I am connecting my compensator at the point of common coupling, what is happening is I am connecting indirectly. When you turn on the switches, you are connecting VDC across these point of common coupling voltages. So therefore, the design of the DC link should be such that the voltage of DC link should be greater than the peak voltage that could occur at this point of common coupling. So if my grid is a 230 volt AC RMS grid, then I know that peak voltage that could occur across it is 230 √2 for a sinusoidal waveform. So using that value, we calculate the value of the DC link. Then there is ripple filter. As I mentioned, the purpose of ripple filter is to absorb the harmonics. So depending on what frequency harmonics are present in my grid and what frequency harmonics do I want to filter, I will design this RC filter accordingly. Then there is this interface filter. So we know that on one side there is a sinusoidal balanced voltage, and then on the other side there is pulse width modulated voltage. So the reason of putting this filter between if we would have directly shorted, then at point of common coupling we would have had pulsed voltages, that is switched voltages, which is very damaging for our loads. So in order to filter those voltages and have a smooth variation in these voltages, we have put an interface inductor here. This absorbs the voltage difference, magnitude difference between the pulse width modulated voltages and the sinusoidal voltages. So when you look at the DC bus voltage, then this formula came from the fact that when we have line-to-line voltage is given for a three-phase system, the phase voltage is obtained as line to line by √3, right? Phase is equal to line to line voltage by √3. Now, in order to calculate the peak value of this phase voltage, I will multiply this phase voltage by √2. Okay, and then my VDC by 2 should be greater than equal to the peak voltage at the point of common coupling. And why VDC by 2? Because when you have, let us consider three leg converter. Okay. So in order to analyze this converter, we analyze it like this. Okay. So we call this point O. Let me say this is as point A, point B, point C. So if I say this is VDC, then this is VDC by 2 and this is also VDC by 2. So the voltage at node A, suppose this is switch 1, switch 2. When switch 1 is on, voltage at point A is VDC by 2. So this O is the fictitious reference point. In reality, you just put one capacitor of value CDC here. But in practicality, but while doing the analysis, in order to, we need some reference, right? We could take this as reference or we could take this as reference. So when we take point O as reference, we get sort of intuitiveness in our expressions. So that is why we take point O as a fictitious reference point. Fictitious means it is not existing in practicality. In practicality, I am putting only one capacitor, but just for the sake of analysis, I am considering it as two capacitors. So when switch 1 is on, the voltage at pole A is VDC by 2. And when switch 2 is on, voltage at switch A is minus VDC by 2. That is what I was telling, right? So these voltages are switching between plus and minus VDC by 2. So this is the pulse width modulated voltage. Now, yeah, so that is why at one point of time we want this VDC by 2 to be greater than the peak voltage, so that the current always flows from the compensator to the source and not the other way around. So that is why this is the minimum inequality condition that we need to think about. VDC by 2 should be greater than or equal to, it should never be less than. Otherwise, current will flow from the source to the compensator, which we don't want. We want the compensator to support the grid, not the other way around. So that is why our VDC should be greater than two times the peak voltage. And we know that the peak voltage is root 2 into V phase RMS, and we know that V phase RMS is VLL by root 3. So that is how from there you will get this expression. And M is the modulation index, which is the ratio of the peak voltage to the 2 VDC by 2 for this 3-leg or 4-leg converter. So using that, you obtain the DC bus voltage as this. So for different values of line to line voltage and modulation index, you can obtain the DC bus voltage. Now for selection of DC bus capacitors, this is one expression for 3-phase 3-leg converter. Here we are doing energy balance equation, right? So what we are trying to do is we know that the energy stored in the capacitor is given as half CV square. So what happens is in a DC link, whenever my compensator will be working in transient conditions, right? So the purpose of my compensator is to give the instantaneous energy that is required by my system. So when I am giving the instantaneous energy to the distribution system, then what is happening is that my capacitor DC link voltage is getting changed. So let us say at time t1 I am giving the energy from my electrolytic capacitor to the distribution system. Then what is happening? My DC link voltage reduces from VDC to VDC1. Then the energy that I gave is half C VDC square. This was the energy that was available in my system before, minus half C VDC1 square. This is the energy that I gave to the system in order to fulfill a transient condition which required this much power. How much power? For a 3-phase system it will be 3 into voltage into current, 3 times, because it's a 3-phase system. So 3 times phase voltage into current. Now A is an overloading factor. Suppose during transients we all know that we consume a lot of more current. So if I am taking a factor of 20%, that means I can, if my system is 10 ampere system, then I will be consuming 20% more. That is, I can go up to 12 amperes during my transients. That is the significance of overloading factor. Okay, so this is the current overloading factor. And then there is the time factor. That is how much time I want this voltage to be maintained again to the reference voltage. In how much time do I need to supply this amount of energy? So this is time t. And K1 is another parameter which is which is given as the variation in energy during dynamics. So this is full energy that I have. And how much energy do I want to give? Do I want to give 10% of this energy or 20% or 30%? So I can set these values. So whatever is the purpose of putting that compensator in that location, I can, depending on that, I can calculate A and K1, and then rest of the parameters are already fixed. So this is basically an energy balance equation. Okay. So this is for a three-phase three-way converter. Then this is again for an inductor, we know that it's V equals to L di by dt. Using that same expression, you can obtain this equation. This is a standard equation for three-phase three-wire system. Then for the ripple filter. So we know that the ripple filter is supposed to take in it the high frequency components, right? I want that my high frequency component should flow through the ripple filter. Then while designing the ripple filter, what I will do is I will design the ripple filter in such a way that its impedance to high frequency components will be very low, so that during yeah. So suppose this is my RC filter. Okay. Now this is connected to my grid. This is my source. This is my load. Okay. And there is a compensator here. Now because of the presence of compensator, here high frequency noise is coming. High frequency voltage is coming, right? Because of the high frequency voltage, there will be some harmonics here. So this branch of R, RC and CC is offering certain impedance, right? Because XC is equals to 1 by omega C. The reactance of the capacitor depends on frequency. So I will design the value of this capacitor in such a way that it offers low impedance. That means ZC is equals to RC plus 1 by J omega C is very less for high frequency components, and ZC will be very high for low frequency or fundamental frequency components. That means I want this to be a very high impedance branch as if it is not existing in my circuit when fundamental frequency components are going in, and I want the impedance to be very low value so that all the high frequency components can flow in this branch. Okay, so that is how we design the ripple filter. Okay, so for the ripple filter, you can see that the time constant should be much less than the switching frequency. When the time constant will be much less than the switching time, then the frequency components that this ripple filter will consume will be much higher than the switching frequency components. That means all the multiples of the switching frequency will be absorbed by this ripple filter. Okay, so this is
And
how.
is there any reason to take, madam, 10 that RC time constant value TS by 10? Is there any reason, madam?
So normally what we do
Exactly 10.
in control systems design, whenever we have to when we have to finalize the bandwidth of a system or anything, then we consider it's like you could have considered it by 9, by 8, anything. But normally as a just engineer's judgment, we take it by 10. Not a hard and fast rule. Only the fact is that RC should be RC, the time constant of the RC circuit, that is R into C, should be much less than the switching time.
Okay, ma'am.
That is the only constraint. Okay. Now, selection of voltage rating of the solid state switches. So the voltage rating will depend on DC link voltage and the overshoot in the DC link voltage. So we are connecting the switches. So okay. So this is my leg, okay, and this is my capacitor. So the voltage of this capacitor is VDC. Now, suppose this is S1, this is S2. So when I am turning on switch S2, what is happening is the switch S1, when I am turning this on, the switch S1 has to block VDC voltage, all the voltage. So the circuit after turning on switch S2, my circuit looks like this, right? That means voltage across switch S1, VS1 is equals to VDC. That means S1 switch has to block all the voltage that is given by the DC link. That means all the overshoot, undershoot, whatever is the voltage at DC link, it has to block. So therefore, this is how we rate the switches. Similarly, the current. So when we know that the current waveform is something like this, and this is the steady state value of the switch current that we obtain. So the ripple current, the peak value of current, steady state peak value of the current, plus the ripple, maximum ripple that I'm expecting, with a safety factor of 0.25 times. 25% extra we are taking. Why? Because it's just a factor of safety thing. So you could take it 1.2 times, but normally in industry we take it 1.25 times. Okay. Then sir has given the design comparison of lot of different configurations. That if you go for a two-leg, for a similar rating, two-leg voltage source converter, what will be the ratings of the component? For three-leg, what will be the ratings? So based on, so whenever you have an application, this kind of analysis should be done. And then based on what is the most, now here sir has mentioned only the ratings. Based on these ratings, you could find the cost. Then you could compare the cost of all these three converters for the same rating compensator. So based on that, you could make your final decision on what kind of topology are you going to use in your kind of compensator. Okay. So depending on these things, you can have a look there. And then there is design of three-phase four-wire statcom. Then the equations for three-phase four-wire are almost similar. The only difference in three-phase four-wire is the derivation of capacitor. So what happens in three-phase four-wire is it could be almost similar to a design of a single-phase converter. So what happens in single-phase converter is when unbalance occurs due to the presence of unbalance, a second harmonic component appears in the DC link voltage. So you could do a derivation, a theoretical derivation, or you could do a simulation in order to understand the second harmonic component. So what happens is whenever there is an unbalance in the system, then a second harmonic component appears in the DC link. So the current that is flowing into this DC capacitor contains second harmonic component. So instead of using energy conservation, we use the design of the capacitor in such a way that it can handle the second harmonic component. And the voltage ripple does not exceed beyond our permitted limit. So we use this capacitor DC equation in order to obtain the value of capacitor in this case. In other cases, the second harmonic component is not present, but in four-leg converter it is present. So we have to design accordingly. Similarly, then the value of, since it's a four-leg converter, the value of, in neutral leg also we have an interface filter. But design equation of both the neutral leg and the phase leg are different. So depending on the three-leg or four-leg configuration, you design the neutral, the leg, the inductor and the neutral. And the design of rebel filter is same as for the three-leg converter. Voltage rating for the switches, current rating, both of these are also same. As let us also discuss the design of three single-phase voltage source converters. This is also very similar to the four-leg converter. Okay. Now, when we talk about the control, now I have the hardware ready. Now I have to code the control algorithm inside the DSP which are present in these compensators, right? Now the control algorithms that are available are of two types, mainly categorized into two categories. One is time domain, another one is frequency domain. So when we talk about time domain, it means with respect to time, and frequency domain means we transform the time domain. So any signal that we obtain is a time domain signal, because any signal that we obtain has some magnitude at some instant of time. So all our real-time systems are time domain systems. Now we convert it into frequency domain, and sometimes when we convert it into frequency domain, our analysis becomes simpler. So that is why we convert the time domain signals into frequency domain signals. Okay, so that is the purpose of this. So these are few examples of both the categories, and sir has explained the few time domain control algorithms. Normally, what happens with frequency domain is since we are first first taking time domain signals and then converting them into frequency domain signals, additional time is required, right? So definitely when we talk about high frequency compensators and we want to compensate the system in a dynamic manner, then we cannot say that I can take 1 second in order to compensate a 20 millisecond cycle 50 hertz sinusoidal. So when we say 50 hertz is our grid frequency, that means the time constant of one sinusoidal cycle is 20 milliseconds, right? 1 by 50 hertz. So this is 20 milliseconds. So the time constant or the response time of my compensator should be less than 20 milliseconds in order to be more effective. So when I'm talking about this low response time, I cannot afford to have time delays because by the time I actually give the output of this compensator, my load nature might have changed, right? So I need to act quickly on this. I cannot have a lot of delay. So that is why frequency domain control algorithms had a lot of drawbacks before, but now because of the high bandwidth DSPs which are available, they operate at a very high clock frequency, and because of those high frequency operating DSPs, nowadays frequency domain methods have also become usable. So Sarah has discussed few time domain methods. So one is the first one that we discussed was unit temperature PI controller based control algorithm. So in this PI controller based algorithm, what happens is we directly go to the block diagram and have a look at what happens. Okay. So here we will sense the voltage at the point of common coupling. Okay. And then based on the voltage that I obtain at the point of common coupling, I will derive unit templates. Unit templates means unit amplitude signals that are in phase with VSA, VSB, and VSC. So what I am doing here is, suppose this is my VSA, this is my VSB, and this is my VSC, and it has some amplitude of 230 to, and some unbiased will also be there, right? It will not always be exactly 230. It might be 200, it might be 250, and so on, right? So I am obtaining a sinusoidal wave of magnitude unity, which is in phase with this VSA, VSB, VSC. So this unit amplitude thing is called unit template, USC. So because I want the phase, because since I am operating in unity power factor mode, that means I want my source current to be in phase with my source voltage. So when I talk about this compensator design, so there is source, then there is load, and then there is compensator. Now you all might have heard about closed loop systems, right? So in closed loop system, you always have to provide a reference. That means, so there are two types of systems. I'll just briefly explain you: open loop system and closed loop system. So what happens in open loop system? Suppose I am boiling the milk in my house. Then what I am doing is I turn the gas at the maximum position and then I keep on monitoring, right? So normally what happens is I look at the milk and then I keep on checking it whether the level is rising or not. So the moment it rises, I turn off the gas. But now this would have always worked for I could in order to make suppose I want to do something, I don't want to stand there all the time, and I time it out to be 5 minutes. That my milk is taking 5 minutes to get boiled completely. Then, do all the time does it take 5 minutes? No, right? Do you know why it does not take the same time all the time? Why does our milk boil at different times? Can anybody answer this?
What is, madam?
So if you are boiling milk, okay, then
Okay.
sometimes your milk takes four minutes. Sometimes it takes 5 minutes. Sometimes it might take 4.5 minutes.
Humidity conditions, environmental conditions is there, madam.
Exactly,
Sometimes
exactly. Yes. So
means
there
what
are a
you are
lot of
using to heat that milk. What type of device you are using? Means. That is
Yes.
also one of the reason.
So, yes. So, that time we as human beings act as a closed loop sensor. What we do is we keep on monitoring, right? We are using our eye sensor there to monitor the height of the milk that time, right? So that is how our system becomes stable. Otherwise, if in an ideal condition I measure that at 25 degrees Celsius and 1 bar temperature, that ideal temperature and pressure, if my milk boils in 5 minutes and I leave for 5 minutes, my system will become unstable. It won't be a stable system. The milk will come out. But if I stand there and use my eyes in order to monitor it, then I am closing the loop. Initially, it was an open loop system, and open loop systems are unstable because, as Venkat sir mentioned, the environmental conditions are changing from time to time. They are not constant. They are not 25 degrees Celsius in 1 bar. They are something else. So I need to change this time depending on the environmental conditions. So therefore, I need to close the loop. And while I am boiling the loop, I am closing the loop using my eye sensor. Similarly, in this system, what I am doing is I want to measure the load current and then supply the bad part of the load current using the compensator. That means what I will do is I will first sense I will first sense this load current, right? It will be some load current which will have both DC component and AC component. This AC component is the bad part, right? That I want to give. Say, let me assume that this AC part is the bad part of the current and DC part is the one that I want to transfer. Then this AC part of the current I will give as a reference to this compensator. IAC, this is will be my reference, compensator reference. Then this closed loop, this is how a closed loop system looks like. So suppose I have a plant and it is giving some output. So I will measure this output using a sensor. I will give a reference here. This is a comparator. Then using the sensor, there is some output which I am sensing using the sensor. I am comparing it with the reference. Then reference minus the output gives me error. Then this error is being given to a controller which gives an output to control the plant. Initially, I had in open loop condition, I had a plant, I had an input and an output. So for every input, I had an output. But I don't want to stand there all the time, right? I don't want to put a brain there all the time. I want it to be closed. That means whenever some change happens in the output, suppose I want the output to be 700 volts all the time. Then I can just put a feedback loop, which is called a closed loop system, and then make sure that by giving reference 700, this output will always be maintained at 700. This is how the closed loop system works. And we can make the system stable, much more stable, because our real systems are not stable, open loop systems. So we can make them stable. So here I will give the reference as the bad part of the current, and I will make this will be my compensator current which I will be sensing, and this will be my compensator reference current, which will be equal to the bad part of load current. So what I am doing here is I will switch the switches of my converter in such a way that it generates the bad part of the load current. And how is this happening? By setting a reference. So that I will sense the load current. I will calculate the bad part of the load current from the sensed current, and then set the reference of the compensator as the bad part, so that my compensator supplies the bad part of the current. Is this clear?
Okay, madam.
Okay. So now there are two ways. I could either find out reference for compensator, or I could find out reference for source currents. So when I am using this comparator in closed loops, so I could have here I supply reference and then I supply sensing, or I could have here I compensator reference or I compensator sensing. So which one to use? That is the question we are trying to answer. Then what is happening here is, when since I'm doing a compensator design, right? My compensator is the one which is helping me. So logically, I should go for this design. But what is happening here is, since the nature of my compensating current is highly varying in nature, it is lot of sharp edges are there in the ripple, in the waveform of the compensator current. Whereas when we talk about the sinusoidal current, it is very slow varying current. It is kind of ideal. So therefore, this is called this type of technique is called direct current control, because we are switching the compensator based on the compensator reference. Whereas this is called indirect current control. So by comparing the supply current with the supply reference, I am generating the switching pulses for the compensator. So therefore, just for the sake, because the compensator current is highly varying in nature, whereas sinusoidal current is easily varying. Now, what does the variation have to do? So this loop which I just mentioned to you, it is operating at some frequency, right? As I mentioned, that 20 millisecond is the cycle of 150 hertz cycle is 20 millisecond. So since I need to operate at that cycle, what I need my system to do is, I need to make this control loop work very fast. That means I want it to track the system very fast. Now this bandwidth is the frequency of the system. Okay, so if my reference is very fast changing, that means it requires very high frequency to operate. Whereas this works with low frequency. And when you go to high frequency, there are a lot of complications that come into picture. So it is much more easier to design a low frequency. It is easier to track a slow varying signal than to track a fast varying signal. So that is why we choose to go for indirect control, that is controlling the supply current rather than controlling the compensator current. That is why in all the algorithms that Sir has discussed, Sir is finding out the supply reference current instead of the compensator reference current. Okay, so we in all the algorithms that we are using, we will be using the indirect current control. Okay, so in this first algorithm, what is happening is, so as I mentioned, unit templates, right? So USA, USB, and USC are the unit templates. So now what is happening is, now any signal, this is the reference that I want, right? This signal is having amplitude and phase, both two things, right? So in order to get the phase, I already obtained the unit templates because I want unity power factor. So unity power factor means I want these currents ISA to be in phase with VSA or USA, and ISB to be in phase with ESB. That means I will just multiply the amplitude with these unit templates. Now from where the amplitude comes? So this ISPP star is the amplitude. Now from where is it coming? It is coming from the closed loop again. So this controller, as I mentioned in the previous this closed loop, there is this controller. So normally the most conventional controller that people use is the PI controller in order to obtain zero error. So this is VDC, which is the sensed DC link voltage, and then I am using a low pass filter because as I mentioned that there might be a second harmonic current in the DC link because of the presence of unbalanced load. So therefore, we need a low pass filter for the DC link. And then there is this reference. Suppose for our system, 230 volt system, we have calibrated the DC link voltage as 700 volts. So I set the reference voltage as 700 volt, and here will be my sense DC voltage, and this will give me how much current do I need to draw from the source in order to maintain the DC link to its value. Now, why I am using VDC here? Because whenever my D statcom is supplying any kind of transient, it is taking the energy from the capacitor because that is the only energy storing element that is present in my compensator, right? It's a reactive compensator, it's not an active compensator. That means there is no battery present inside it. It can deal with only reactive powers. So the only energy storing element in my compensator is capacitor. That means the moment some problem comes, they will ask for energy from the capacitor. So when my distribution system is going through some transients, it will ask the D-statcom to give some energy. So capacitor will give. So when capacitor will give its energy, what will happen is its DC link voltage will come down. And the moment the DC link voltage comes down, this circuit will start operating. This error which is coming here will no longer be zero. This will become non-zero, and then this controller will operate and it will give references. And then based on these references, what I will do later on is I will compare these references with the actual supply voltages, and using those current controllers, I will be generating the pulse width modulated signals for the switches to operate, gate pulses. Basically, whenever there is a switch, you need to give it on off signal. This on off signal is called gating pulse. So these gating pulses are obtained by, so I obtain these references, right? These ISA star, ISB star, INC star. So this ISA star I will give it to another closed loop comparator. This will be my sense supply current. I will give it to a controller. This controller will give PWM signals to my inverter or the 4-leg converter, and this will be the closed loop. This is the another current loop that will be present in my circuit. So this is how this is what this control algorithm is depicting. Okay, so now using this control algorithm, what we did is, since ISA, ISB, and ISC are in phase with VSA, VSB, and VSC, I am able to obtain the unity power factor mode, operate in the unity power factor mode. And also, I am able to compensate for any transient that has occurred. So whenever my D-STATCOM will supply any kind of errors, then my voltage will reduce and this loop will start operating, and then my reference. So this ISA star, ISB star, and IC star are continuously changing. They are not fixed. Okay. So depending on what is the DC link voltage, so whenever compensator is operating, DC link voltage will change. Whenever DC link voltage changes, these reference changes, and when these reference changes, then the gating pulses to the switches changes. Then switches will operate differently depending on what is the reduction, and it will operate until this error becomes zero. And the moment this error becomes zero, this compensator will stop operating. Okay, so these are the mathematical equations. So the sir has assumed that it is easier to build. So instead of using 3 voltage sensor for all 3 phase voltages, what we could do is we could measure line to line voltages, and then from those line to line voltages, I could obtain the phase voltages. So instead of 3 sensors, I could just do with 2 sensors. So that is why sir is doing this. He is sensing the voltage between the line AB and the line BC, and then using those line to line voltages, he is obtaining the phase voltages. And then using those phase voltages, we keep calculating the peak voltage at that point of common coupling. And then in order to obtain
Madam,
the unit.
that last component VSCAB, VSBC, and last one is 0, madam. Why it would be taken 0, madam?
Which one? This equation?
Here, yes, madam.
No. So actually, okay. So whenever in matrices you need 3 cross 1 matrix, and this is 3 cross 3 matrix. So this has to be a 3 cross 1 matrix in order for this
Further
equation to
told
be balanced.
you are taking that 0. Yes.
Yes. So if you write the equation for this matrix, from where did it come? Is you had line voltages and you tried to calculate the phase voltages from that. So you have 2 equations. One is VSA plus VSB. We are assuming balanced voltages first of all, and then another equation is VSAB is equals to VSA minus VSB, and VSBC is equals to VSB minus VSC. So using these equations, you will be able to obtain these equations, and then you can write it in matrix form. So this is how it will come. And this last thing is 0 because we need to maintain the matrix dimensions. Is your doubt clear,
What
sir?
it will happen? Here you have to take in 0, madam. If you take in a VSCA, what it will happen, madam? AB.
VSCA. Okay. So, so why we are not taking VSCA is because here, okay. if I have, okay, so if this is my three phase lines, okay, this is A phase line, B phase line, and C phase line. There are, and this is my point of common coupling. Okay, then I have two options. One is I can put, suppose this is a four wire system. Okay, then I could put voltage sensor between VA and N, VB and N. Voltage sensor has to be, in order to measure voltages, you need two nodes. That is clear, right? For current, you can you can measure in one path, but for voltage, you need two nodes. So, if I am measuring phase voltages, that is VSA, VSB, and VSC, then I need three sensors. Now, instead, if I just measure VSAB and VSBC, then using this matrix, I am able to obtain the values of VSA, VSB, and VSC, which is what I need. I needed to measure VSA, VSB, and VSC, but since, in order to save the cost, instead of using three sensors, I am just using two sensors.
Okay, now I understand.
Okay, so it's not that you can have a matrix in which you can, these parameters will change. You, if you have VSAC, but the only purpose
Yes,
of
madam.
not measuring this is in order to reduce the number of sensors. Okay,
Okay, ma'am.
so okay. So now you have now using the line voltages, you have obtained the phase voltages using this matrix. Now once you have the phase voltages VSA, VSB, and VSC, you will find unit templates by dividing with the peak magnitude. This is the peak magnitude, and this is how we obtain the unit templates. Now I want to obtain the magnitude. Now I have obtained the phase, that means the angle by which I multiply. Now in order to obtain the magnitude, I will obtain it from ISPP star, which is this PI controller, and this is the discrete equation of the PI controller. This is the proportional constant, this is the integral constant. So if you want, we can discuss these in detail, but this is just the discretization of PI controller. Okay. This is the comparator, VDC reference minus VDC, which will give me VDC error. Then PI controller is basically proportional plus integral controller. That means it has a constant term and then it has an integral term, Kp plus Ki by S. S is the transfer function constant. So S is equals to j omega here. Okay, and then this Kp and Ki. So this is this Kp and this Ki is this Ki. So if you write this Kp plus Ki by S transfer function into discrete domain, you will obtain this equation. And then in order to obtain ISA reference, ISB reference, and ISC reference, just multiply the magnitude of ISPP, which you will obtain from here, with their respective unit templates. So this is how this method works. And then once you have obtained these, you know what to do, right? You will do this. Supply the ISA reference with ISA, ISB reference with ISB, and then you will again put a PI controller, and then output of that PI controller will generate the gating pulses for our converter. So this was our unit template based method. Then the same method can be used in so far we used it in unity power factor mode. The same method can be used in voltage regulation mode. So for the voltage regulation mode, the only difference will be that apart from the positive apart from the in phase component, we will also be sensing the quadrature components. Because for unity power factor mode, we know that we directly know that in unity power factor mode, reactive power is 0. So we didn't need any quadrature components. Whereas in 0 voltage regulation mode, reactive power is 1 0. That means in 0 voltage regulation mode, there is no source, there is no load, and this is the point of common coupling. Then the compensator supplies reactive power in order to maintain this point of common coupling voltages to the desired value. That means reactive power is no longer 0. So here, using the VDC references, I am calculating ISPP star, which is the magnitude of my supply current, and then this is giving me IS references for in phase components, and then there will be another IS references for quadrature components. This will be responsible for voltage regulation. So this is coming from VSP star. So VSP star is this parameter, that is the peak valued point of common coupling. So from this parameter, we will give it to a POI controller. It will give me the magnitude of VSQ star. And then using my in-phase unit templates, I will be using a block diagram which will a block which will convert this in-phase unit templates into quadrature components. Quadrature components means components which are 90-degree phase shifted, right? So if my USA is like this, then USAQ, okay, SAQ is the name. So USAQ will be 90-degree phase shifted. Okay, so these are called the quadrature components. So I generate the quadrature components for this, and then these will be used to multiply with the amplitude which we just obtained by comparing the peak of point of common coupling voltages. Then this is the in-phase component, is the quadrature component. By using these two components, we will be able to apply the supply reference currents. And then when these supply reference currents will be compared with the actually sensed supply currents, then I will give them to their respective current controllers, which could be a simple PI controller, or there are a lot of high level controllers available, from simple controllers to neural network based controllers. So, depending on any kind of controller, you will be able to obtain the gating signals. Okay, so this is how you can obtain, you can use the same method for different modes, in different modes, for unity power factor mode or zero voltage regulation mode. Okay, so these are the equations for the low voltage regulation mode. Then there was some power balance theory. So in this power balance theory, what is happening is you are calculating the real power, you are calculating the power, and then instantaneous power you are calculating, and then that instantaneous power has both AC and DC components. Then based on those AC and DC components, you are deriving the supply reference currents. So here what is happening is, using the point of common coupling voltages and load currents, you are finding the value of instantaneous power that the load needs. Then using a low pass filter, you are filtering the AC part and getting only the DC part. DC power is the only effective power that is being required by the load. So this DC power, using this DC power, you are calculating the DC component of the load current that is required. Then there is another component, in phase component, that you need is to maintain the DC link. So this part tells the requirement of the load, and this part tells the requirement of the compensator. So when you have a source load system, verbally if you observe, then what all things are required to be done by a compensator? The compensator needs to supply the bad part of the current. Apart from that, there will be losses in the compensator, right? So compensator will have to take some active power from the source in order to maintain that losses. That means that whenever there are some losses in the switches, those are real losses, real time losses. So in order to take care of those losses, we take power from the grid. So that is why we are using a summer here. So this DC link voltage maintenance comes, this active power will also be a part of the in-phase current component. Similarly, when we talk about the quadrature component, then again there are two components. That means this was a diagram for active power. Now similarly, when we talk about the reactive power, we have two components. One is the load requirement of the reactive power. So this is the channel for load reactive power, and this is the channel of reactive power requirement by the grid in order to maintain the point of common coupling voltages. So this is a very in-depth block diagram. So if you look at a raw block diagram, then this part is load power. This part is power required to maintain DC link. These both powers are active powers. Therefore, their components are used for the derivation of ISPP star. And then there is this is load active power, and then this is load reactive power, and this is the reactive power required for voltage regulation at point of common coupling. In order to do the voltage regulation at point of common coupling, this is the part. So these both are added, and then they both are used in the calculation of ISQ star. Okay, So then once we have obtained both these current components, we can again use their quadrature and templates to obtain the IS, their respective current components. Then we can add both the current components, and then we can use our current controller to obtain the gating pulses for the converter. So this is again similar principle. So similarly, sir has discussed I cos psi based control algorithm, and then there is current synchronous detection control algorithm, and there is IRPT based control algorithm, instantaneous reactive power theory based algorithm. Here, here we are converting the ABC signals into alpha beta signals and writing the power equations in terms of alpha beta components. So this was, I think, very simple. Similarly, there was synchronous reference frame based theory. So synchronous reference frame is in DQ domain. That means we convert the ABC signals into DQ signals, and then we generate the gating pulses for our system. So these were, then there is instantaneous symmetrical component. So there we obtain the symmetrical components of our system. That means positive sequence and negative sequence components. So you can go through these methods. Actually, there are a lot of methods, so I will not be able to take up all of these in the class. But in case you have any doubts in any of these methods, then you please feel free to ask. We'll have a discussion in the class, okay? So then, after discussing a lot of methods, all the methods that sir has discussed were from the time domain methods. So, okay, so based on so after discussing the methods to implement, he has discussed the performance curves. So how does the performance curves look when you look it in the DSO or any kind of waveform observer? So these were the waveforms for unity power factor mode, and then for zero voltage regulation mode. So these were very pretty clear, I think. So you could either obtain power factor correction mode or load balancing mode or zero voltage regulation mode. Okay. So depending on, so you need to, so what sir has done is I'll just focus on one such waveform. So what is happening here is, initially, this is how I am varying my load. So initially my load was balanced. Then I made the load of one phase to go to zero during this time to this time. Then I am again giving the balanced load. So when my load is unbalanced from this to this time, what is happening is, because of this unbalance, in order to make the source, because of this unbalance, there is a bad part of load current. So my compensator started getting activated and started giving the bad part of the current in such a way that the source current is still balanced. If I would not have had the compensator in picture, then all this bad part of the current has to be supplied by the source. And the problem with this would have been that when my system is when this is my source and this is my load, if my source is directly supplying to load, then all this bad part of current would be coming from the source. That means the nature of voltage at the point of common coupling will be highly distorted, because voltage at point of common coupling is equals to Vs. Suppose my generator is having 30 volt, it is generating properly to 30 volt, but Vs minus Is into Zs. So this source impedance is the problem. So when this source impedance comes into picture, the voltage at point of common coupling will be highly distorted because it is depending on the Zs magnitude. And this Is, if Is current is non-linear, then point of common coupling voltage will also become non-linear. That is why instead of directly letting the source supply to load, we connect a compensator here near to the load so that the compensator can supply the bad part in such a way that my source current is beautifully balanced, which can be clearly shown. If this wouldn't have been present, then my source current would have looked like this, which is highly unbalanced and non-linear, which I don't want. Okay, and you can see that what is happening here is, so when I am removing the load from my system, my voltage is increasing. It is getting an overshoot, right? This is an overshoot of the DC link voltage. And when I am putting back the load, my DC link voltage is getting reduced. So this is what we normally expect from any electrical system, right? The moment I the moment I switch on the load, my voltage at the point of connection decreases, and when I remove the load, the voltage at the point of connection increases. So that is how normal system works. So this overshoot and undershoot are because of those. And since I am operating in zero voltage regulation mode, you can see that Vs is very close to the, so this actually it should have been shown in a much more, maybe a colorful waveform. But yeah, so this straight line is there which is giving me Vs peak, which is the voltage at which I want to regulate my voltage. And then there is slight deviation because of the unbalanced load, and then it again came back to the VSP level. So this is what is shown in this waveform. That means my system is perfectly tracking. Whereas in unity power factor mode, if you will see, then Vs is not perfectly tracking. Look, there is deviation, right? And here it is perfectly tracking. That means zero voltage regulation mode is properly working. So this is how you analyze the working of any system from its waveforms. Okay. So after that, sir has gone through few numerical examples, and so will we. So I have prepared few questions for discussion. If you don't have any doubts in this, we'll move on to that discussion. Any doubts from the theoretical part that we discussed?
No, madam.
Okay, so I'll move on to the. So this is our third numerical session. Let us get started. So we have 10 questions. Let us solve them. So I am solving at a pretty slow speed. If you want, you can solve together. Okay? So in the first problem, there is a single phase load with impedance 20 plus J18 and has an input AC voltage of 220 volts and 50 Hz. It is to be realized as unity power factor load on the AC supply system using pulse width modulation based D-STATCOM. Calculate the VA rating of the compensator. So there is an AC source which is 220 volt 50 Hz, and then there is a load with magnitude 20 plus J18 ohms. Okay, and then we are converting a compensator in shunt. Now we want the system to operate in unity power factor mode, and we want to find the VA rating of the compensator. Okay. Now we know that the voltage rating of the compensator is very clear. It is connected in parallel with the supply voltage. Will be 220 volts. Now we need to calculate the current rating of the compensator. Now we know from the definition of compensator that compensator has to supply the bad part of load current, right? So load current has two parts. One is active part and reactive part. So we have to supply the reactive part of the reactive part, that is the bad part of the load current. So that means my compensator current is equals to bad part or reactive part of load current. Okay. So now that means I need to calculate my load current. So my load current is V by Z. V is 220 by Z is 20 plus G18, which gives me 8.176 angle minus 41.98 degrees. This is an angle. Okay. Now this has two components, cos theta component and sin theta. Now I know that my compensator has to supply the reactive part of load current, which is higher sin theta, right? So my IL magnitude is 8.176 and sin theta a sine of 41.98 degrees. So this I compensator will come out to be 5.47 amperes. Therefore, my VA rating of compensator is equals to VA is voltage into current, 5.47, which comes out to be 1203.4 volt amperes. Wasn't this easy? Just try to understand what is the purpose of the compensator to supply the bad part of load current, okay, or the reactive part. So whenever you start from that, step automatically flows. Just focus on what you have to calculate and what is the purpose of the compensator. That's it. Let us move on to the second problem. So again, there is a single phase AC supply which has AC mains voltage of 230 volts at 50 hertz and feeder impedance of 1 ohm resistance and 3 ohms inductive reactance, after which a load of 4 kVA 0.8 lagging power factor is connected. If a PWM based D statcom is used to raise the voltage to same as input voltage, calculate the VA rating of the compensator. So VS is 230 volts and 50 hertz. Again, we have to calculate the VA rating, but this time there is a source impedance present, which is 1 plus J3 ohms. And the load is 4 kVA 0.8 lag load. So when you are connecting a compensator, so here we have to raise the voltage in such a way same as the input. That means we are doing voltage regulation. So the aim here is changed. Initially we were doing power factor correction. Now we are doing voltage regulation. Okay. So first of all, we will see what is the reactive power requirement. So we need to do two things here. We need to compensate. So now compensator has to give two components of reactive power. Compensator has to provide two components. One is load reactive power. It has to supply the reactive power that is required by the load. And then another component is reactive power for regulation of point of common coupling voltage, PCC voltage. So there are two components now. So first let us calculate load reactive power. So we know that load reactive power is equals to S into sine theta. Cos theta is 0.8. It is given in the question. So S is 4 kVA. Sine theta is 1 minus cos square theta. And cos theta is the power factor, which is 0.8. It will come out to be 4000 into 0.6, which will be 2400 watts. This is, let us say, QL, that is the reactive power required by the load. Now, in order to calculate the voltage, the reactive power required for voltage regulation, we have already derived the standard equation, which is RS squared plus XS squared into Q squared plus 2V squared. This can be derived using the same condition that Vs, magnitude of Vs is equals to magnitude of Vs, Vs is equals to magnitude of Vl. This is a quadratic equation in terms of Q, and this is a constant term. This quadratic equation, once you solve by putting all the values that are given in the question, you obtain Q as minus 1456.08 volt amperes. So you can solve this in a scientific calculator. It's a simple equation. Just put the values of all these components depending on, this is a standard equation we have just derived in the previous class as well. Okay. So now this is the reactive power required for voltage regulation. Let me say as QV. Okay. Now the Q of D statcom will be equal to the sum of both, right? This QV minus QL. This is minus 1456.08 minus 2400. So it will be 3856.08. It has to be supplied. Hence negative. You could use any convention, but I would request you to uh, stick to a fixed convention, otherwise you might get confused. Okay. So this is the total reactive power that is to be supplied. This is the total reacting of the compensator. Okay. So first try to
Why
understand the
you are
system.
written here, madam? But you are writing negative q minus q.
Sir, your voice is breaking.
Madam, here Q T start come reactive power for stat come supplied.
Yes, basically, my system has to supply both the powers, right? It has to supply this power also and this power also. So it will have to be the sum of the both, right?
Ah,
Because my
here you
because
written uh, okay, madam.
because my load is also lagging, and by that only, like you can use any convention, but you should understand the meaning of it. Otherwise, you might get confused. Because here our load is also lagging, right? Huh. Here our load is also lagging in nature, and for voltage regulation also we need reactive power. That means both the reactive power magnitude has to be added.
Okay, madam. My idea is means whatever may be lagging or leading, it have to supply the and cumulative manner, both combined manner. You have to supply it.
No, 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 no. So if okay, so right now it got added because both the components, these components which I am talking about here, one and two, both require reactive power. If in case my load would have been a leading load, let us say, okay, this is a lagging load, so it needed reactive power. Now suppose it would have been a leading load, then this leading load would have supplied some power, right? So when this leading load is supplying some power, then my compensator will be supplying lesser power, right? So then in that case it will be subtracted. But right now since it's a lag, so in that case if you add both the reactive powers, your answer will be wrong.
Okay, okay, madam. Now I
Okay.
understand.
So you have to understand this.
Hi, ma'am. Just a minute.
Yes. Yes.
In first problem, ma'am, had a small doubt.
Yes.
How to find RMS value of supply line current as well as RMS value of D statcom line current?
Okay. So when this supply is there, right? So supply.
Hmm.
Okay. Initially, if you say without compensator, my supply, the old value of my supply current will be Vs by Z, right?
Hmm. Hmm.
It
Yeah.
will be when my compensator without this is without compensator.
Yeah.
Now Is new. That means after compensator, my value will be Is old cos theta. Only the active part. That means when I am putting compensator, since my compensator is supplying, the reactive part, that is the IL sin theta part. So my source has to supply only the cos theta part. So this will become our new source current after the addition of compensator. Okay, so understand that way. So when you see
Okay.
these words and understand, then it will be much more clear rather than trying to focus on the formulas that we are using, because you know that in phase component is the actual part. So whenever we draw any kind of phasors, so there are,
Hmm.
if this is my supply voltage and then this is my
Hmm.
supply current, it has two components, right? This is one component and then there is a quadrature component. This vector can be broken down into two components, right? So
Hmm.
this is
Hmm.
is phase and this is is quadrature. So what we say is that is phase component is the only component
Hmm.
responsible for active power transfer, and is quadrature component is not playing any role in the real power transfer. So that means
Okay.
the only power that is contributing is ISP, not ISP. Therefore, when my after therefore using compensator, I am supplying ISQ so that the source supplies only ISP, which is the useful part of the current.
Okay.
Okay.
Okay. So if we want to find RMS value means this IS new divided by root 2. RMS value of D statcom line current.
No, so this RMS value is IS old into cos theta. This is the RMS value only. This is not the peak value.
Okay. Okay. IS new is itself is the RMS value.
Yes, yes. Because you are
Yeah, and
using so the
IS
value
sold
of,
itself is the RMS value. Okay.
yeah, this because we obtain, because Vs by Z, we are using Vs RMS here, right?
Okay. Huh.
If you would use
Yeah.
Vs here, then you will get ISP.
Yes. Okay. Hmm.
Let us move on to the third problem. So, in the third problem, there is a three-phase, three-wire D statcom, which is employed at 400 volts. 50 Hz system is used to provide reactive power compensation for unity power factor of a three-phase delta-connected 24 kilowatt induction motor operating at 0.85 lagging power factor. So there is three-phase, three-wire system which is getting connected to a delta-connected induction motor load, which is 24 kilowatt and 0.85 lagging. And then we have to connect a compensator in shunt with it for unity power factor connection. Unity power factor correction. And we are asked to find the D statcom RMS line current in amperes. Now we know that the D statcom supplies the bad part of the load current. That means we have to calculate the load current and then find the bad part of it. So since we know that this is a lagging power factor, that means it will have both active and reactive part of component. So let me calculate the RMS value of the old current before compensation. So before compensation, P active power is equals to 3 V phase, I phase, cos phi. Active power is given as 24 kilowatt, that is 24,000. 3 into V phase is 400 by root 3. V line to line by root 3 is V phase. And I phase is the one which you want to calculate, and cos phi is 0.85, right? So I phase, which is equals to IS new. Sorry, IS old. That means before compensation. This is IS old. It will come out to be 40.75 amperes. Okay. Now this I phase is I phase old, and therefore I compensator is equals to the bad part of the IS old component, which is IS old sine theta, which is 40.75, and sine theta is 1 minus cos square theta, 1 minus 0.85 square, which will come out to be 21.47 amperes. Okay. Same principle. We just moved from a single phase system to a three phase, and the same principle we were able to use. Now let us move on to the next problem. A three-phase unbalanced delta-connected load with ZAB, ZBC, and ZCA as given in the question has an input line voltage of 415 volt and 50 Hz. It is to be realized as a balanced unity power factor load. On a three-phase supply system using pulse width modulation based D statcom, calculate the supply line RMS current. Now we have to calculate the supply line RMS current. Okay. So the load impedances are 12 plus J9 ohms, 7 plus J5 ohms, 12 plus J8 ohms. Now in order to calculate the supply line RMS current, we need to calculate the active power first of all, because based on the active power, our supply current's magnitude depend. Now, in order to calculate the active power easily for a delta connected system, let us calculate YAB, which is 1 by ZAB, which is equals to 0.053 minus 0.04 J. YBC is equals to 1 by ZBC, which will come out to be 0.095 minus 0.068 J. And YCA will be equal to 1 by ZCA, which is equals to 0.58 minus 0.038 J. Okay. Now we know that the total active power for the system can be easily found by this expression. Now we need to find the total active power consumed by load. So we have conductance part of these admittances, right? The GAB, GBC and GCA. So if VSAB square into GLAB plus VSBC square into GLBC plus VSCA square into GLCA. If you put the values, we will obtain 415 square into 0.053 plus 0.095 plus 0.058, which will come. So this total power, say PT, will come out to be 35478.35 watts. This is the total power. Now, this total power will be supplied equally by all three phases in a balanced manner. So, per phase active power will be PT by 3, which will be 11826.117 watts. Now, we know that ISA will be equal to this active power, basically the magnitude of the current, angle 0. ISB will be equal to P by, this is the peak value, VSP is the peak value of the point of common coupling voltage. The magnitude of all three currents will be same, and they will be 180 phase shifted. So by putting these values, VSP is, it was 415, right? It was 415 by root 3 is VSP. By putting the value of P and VSP, we can obtain the current as 49.358 angle 0 degree amperes, 49.358 angle minus 120 degree amperes, and 49.358 angle minus 240 degree amperes. These are the three supply currents that were asked in the question. Let's move on to the next problem. A three-phase, three-wire D-STATCOM is employed at 400 volt 50 Hz system is used to provide the load balancing and power factor correction of a single-phase 36 kilowatt unity power factor load across two lines. Calculate the D-STATCOM kVA rating. So in this is a three-phase, three-wire system where suppose if these are the three-phase lines, then a load is connected between two lines. And this load is a 36 kilowatt unity power factor load. And then we are connecting a D-STATCOM in parallel with it for power factor correction and load balancing. And we are asked to calculate the D-STATCOM kVA rating. Now, in order to calculate the kVA rating of the D-STATCOM, we need the voltage and the current of the D-STATCOM. Now, the D-STATCOM currents depend on, suppose this is ISA, ISB, ISC, and this is ILA, ILB, and ILC, and these are my compensator currents. ICA, ICB, and ICC. Okay. So using the KVL, we know that the value of these compensator currents depend on source current and load current. That means I have to determine both load current and source current And then using KCL, I can find out the compensator currents. And then once I have obtained the compensator current, I can obtain the rating of the compensator. Now, let us, so we know that before compensation, if we talk about, then my load current, A phase load current is equals to ILAB, which is equal to 36,000, which is the power divided by line to line voltage, because it is connected between two lines directly. So it is the voltage that is applied is VAB, which is 36,000 by line to line voltage, which is 400 volts. So this will come out to be 90 amperes. So this implies my ILA is equals to 90 angle 30 degree and ILB is equals to minus 90 angle 30 degree, because ILA and ILB are line currents. They cannot be 120 degree phase shifted. So when you will convert them into into from star to delta and these configurations, then you will obtain a phase shift of angle 30 degree. So we have obtained ILA and ILB.
Here I mentioned the 30 degrees, madam.
Sorry?
90 at 90. 30 degrees, how it will be, madam? 30 degrees line to line difference, madam. That is.
So in star to delta, so when you convert star to delta, so this is a kind of delta connection, right? With two other phases open circuit. So this is a part of delta connection. So when you are converting, so these are line currents and then these are phase currents. So when you convert from line current to phase current, then a phase shift of 30 degree comes, right? VLL is equals to VL will be rho 3 times. Yeah, this comes, and then there is a phase difference of 30 degrees between the phase quantities and the line quantities. These are the basics of three-phase systems. So that is why an angle difference of 30 degree comes from there.
There is both are in opposite direction. They are mentioned negative over there.
Yes, from the phasors. Yes, minus is coming because you can see here clearly, right? This is a single phase circuit. This is. So minus is coming because this is the current which is flowing. So ILB is equals to minus of ILA. That is very clear, right? Apart from that, this 30 degree came because we are converting a line quantity into phase quantity.
Okay, madam.
Okay. So if you draw the phasor, so this is like a open delta system. Rest where two more loads are open circuit. So when you convert line, so there is phase current in the delta and then there is line current. So when there is delta, so the currents which are flowing here are phase currents, and then the current that is flowing here are line currents. So when you convert these line to phase currents, then a phase shift of 30 degree comes. If you have any doubt in that, then you can write. If you are not able to find any source to understand it, then you can write to me. I can derive and show it to you in the next class. Okay.
Okay, madam. No problem. I can understand, madam. Open delta.
Okay. Okay. So now after compensation, let us find the. After compensation, what will happen is all the source currents will be balanced. Right. So this will be, and it will be equal to P by 3, and we'll divide it by the peak voltage. P by 3 because total voltage will divide into all three phases, and when power divided by voltage, I'll get the current. This is 36,000 by 3 into Vs peak is, it is 400 by 3.
And that is phase voltage or peak, madam?
This is phase voltage. Phase voltage.
Okay, okay, okay.
51.962. So this is the magnitude of my all source currents, and the phase will be angle 0 degree, angle minus 120 degree, angle minus 250 degree. Okay, this is just the magnitude. Okay, so now I know that using KCL, my compensator current is equals to load current minus supply current. Clear, right? Here at node, this highlighted node, if you see, then ISA plus ICA is equals to ILA. Therefore, ICA is equals to ILA minus ISA. It's just a simple case. So from here you get this equation. So just by putting the values that we had obtained before, 51.962 angle 0 degrees. Here I have to put the angle, I cannot just put the magnitude, otherwise I will get erroneous results. Angle 60 degrees. Then ICD is equals to ILB minus ISB, which is equals to minus 90 angle 30 degrees minus 51.962 angle minus 120 degrees. So this will come out to be 51.962 angle 180 degrees. And then again ICC is equals to ILC minus ISC, which is equals to 0 minus 51.962 angle minus 240 degrees. So this will be 51.962 angle 60 minus 60 degrees. So these are the compensator currents. Now we needed to find the VA rating of the D STATCOM. Which is equals to VA into ICA plus VB into ICB plus VC into ICC. VA, VB and VC magnitude is same as the phase voltage, which is 400 by root 3, and ICA we multiply this with the magnitudes. Okay, 51.962 plus 51.962 plus 51.962. This will come out to be approximately 36 kV. This is the VA rating of the D STATCOM. So again, we have a 3-phase 3-wire D STATCOM, which is connected to a 400 volt 50 Hz system and is used to provide load balancing and reactive power compensation for unity power factor of single phase 54 kVA 0.8 power factor lagging load, which is connected across two lines. The same situation which we just saw before, with initially it was unity power factor load, here it's 0.8 54 kVA and 0.8 power factor lagging load. Again, you have to calculate the VA rating of the D STATCOM. Okay, so the only difference here will be between the magnitude of the load currents. So again we have A, B and C, and then there is a load connected here, right? So the magnitude of this, the impedance of the load can be directly found as VAB square by SL, which is 400 square by 54,000, which will be 2.963 ohms. Now we already know the power factor. So we can calculate ZL as 2.963 angle 36.87 degrees. Okay. So ILA is equals to VAB by ZL, which is equals to 400 angle 30 degrees by, this is again a line voltage, right? So we have to consider the angle 36.87 degrees, which is equals to 135 angle 96.87. IL is equals to again minus of ILA equals to minus of 135 angle 6.87 degrees. Now, after compensation, what will happen is all the supply current magnitudes will be same. Which will be equal to P total by 3 for per phase balancing divided by VS phase. So this will be the magnitudes of my supply currents. Now using similar KCL equations, IC is equals to ILA minus ISA, I can obtain the respective currents. Similarly, ICD can be obtained as 124.498 angle 145.705 degree amperes, and then ICC will be equal to 62.354 angle minus 60 degree amperes. So the VA rating of D STATCOM can be calculated as VA into ICA plus VB into ICB plus VC into ICC, which will be equal to the VA, VB and VC are equal and they are equivalent to phase voltages, so they are 73.473 plus 124.498 plus 62.354. So this will give me the approximate kVA rating as 60.119 kVA. This is the kVA rating of D STATCOM.
Ma'am, how to find the RMS value of supply line currents for the same problem?
So these are the RMS value only.
Okay. So that is ILA, ILB and all.
No. So this 62.354 which you see here, this is the supply current magnitude.
Okay.
RMS magnitude.
So here also it comes the before compensation, after compensation like that. That is what you told, IS old and IS new.
Yes, everywhere it will come. So if you initially what will happen here is, if you see IS, because we are putting compensator, right? We are connecting something. Try to understand it in the form of networks. So initially it was only this source was here and load was here. So ISC was 0 initially. ISA was equal to ILA and ISB was equals to minus ILA. Right? And ISC was equal to 0. These were the old RMS values. But after compensation, what happened is, because of the presence of compensator, because of the presence of D STATCOM, all the source current magnitudes became equal and became equal to 62.354 ampere. So this is the change that is happening.
So after compensation, RMS value of the line currents is 62.35. Before compensation, it is that.
It was equal to 135 amperes for ISA, and for ISB it was minus 135 amperes, and for ISC it was 0. So that unbalance has now become balanced. That was the purpose of putting a compensator.
Okay.
Okay. Okay. Any more doubts? I hope you got the questions that you wanted to solve for assignment 4. Now I think you will be able to easily solve.
No. Like in the problem, actually, they have just mentioned calculate the RMS value of supply line current. Then which we have to take for this problem? Either 135 or after balancing it is 62.35. Which we have to put? So they have not mentioned before compensation or after compensation. They have just asked to calculate the RMS value of supply line current.
No, so even here it was the same case, right? So you have to put, since they have mentioned the compensator, that means after compensation.
So we have to take 62.35 only.
Yes.
Yeah, okay.
You have to discuss that in discuss forum, madam. Better to discuss forum, madam.
Yes, whenever you have if there is some doubt where you are not clear about what to mention, then you can ask there. But in this, even we solved, right, this supply current problem. Calculate supply RMS current. So we solved the value of after this only supply current after compensation. Why here? Even if they haven't mentioned before or after, in the flow of the question you see, they have written there was an unbalanced delta connected load, and then they have realized they wanted to realize a balanced unity power factor load using based on the D STATCOM. So they have mentioned it here, right? So because of the connection of D STATCOM, and then they have asked to calculate. Sir, your voice is breaking.
Madam, the load current, madam, not giving that KW or KV for that how to calculate line supply current, madam. Load current they are given 4 unbalanced load 120 amperes, 0.8 lagging, connected between the phase A and neutral.
Same principle, same thing that we did here. Same principle will be used. Just when you are adding
If they
a
mentioned
fourth, so you have to see where the load is connected. Okay, here the load was connected between the
phase and
lines,
neutral, madam.
but when you connect a load to a three-phase four-wire circuit, then the load might be connected between the neutral and the phase. So that time you draw these diagrams
Can you
and try
explain,
to.
madam? Can you
Sorry.
explain, madam, answer?
Since it's an
Can you
assignment
explain
question,
once, madam?
I am actually not allowed to discuss the
Means we have
assignment
to take
questions.
different values, madam. Different values. Just instead of kilowatt kVA rating, you have to tell any load current value, madam. Take any load value. Three phase, four wire.
So similar problem is being solved by in search lecture, so you can look up that problem and also the
No,
same
no, no,
principle.
madam. Not solved, madam. No, no, not solved, madam. That problem.
Not, yeah.
I have just seen the problem.
No, no, madam. He is not is there,
Okay,
madam.
okay, okay.
The
He has
values
solved for three-phase four-wire, right?
unbalanced load of 120 amperes means they are given load current, not using the kW
What I
kVA
can
rating.
suggest you is you can try. You see, sir has solved the problems for three-phase four-wire system. You can using those method or by understanding those problems, try to solve this problem. It is very similar to the one this problem 5 that we had just solved. Right? It is very similar to that. Try to attempt it. In case you are not able to get it, we'll discuss it in the next class.
Means tomorrow is the last day after tomorrow is the last date for
So
submitting
that is why
assignment,
actually
madam.
that is the whole reason they have asked us not to discuss. I cannot change the values and discuss right now because that is an assignment question. So
Means yeah,
I can discuss
one
after this,
twenty
but
amperes.
not before that.
Means I will tell madam is it right way or not? Can you tell you, madam? Here given 120 amperes phase to neutral connected 0.8 lagging. For that you have to calculate RMS value supply line currents. For that, here two components are there, madam. Real power, real current, reactive power component. For that, 120 into 0.8, 96 amperes. That will become supply line currents, madam, 96 amperes.
Yes, so you are given the load current and you are given a power factor. So Is cos theta is the real current and Is sin theta is the bad current. So use the concept of bad current and good current there also. There is no difference, right?
Supply line current, fixed current.
Sir, your voice is breaking.
Madam, is supply phase current or line current, madam? Like
So there, that is where your connections. So when you are connecting a star load to a three-phase four-wire system or a delta load. So depending on the nature of load, you will have to see whether you have to use a line current or phase current.
phase to neutral connected, madam. Load 120 amperes load.
Yes, 120 ampere load is connected. That is a single phase load or a star connected or a delta
Unbalanced,
connected
madam.
load.
That is unbalanced. Unbalanced also, madam.
That means single phase load,
Yes, madam.
and that is connected between two
Suppose
lines
to
or
example,
between line and a neutral.
yes, madam.
Sorry.
Yes, madam. Like will be connected between phase and
Line and
neutral, madam.
neutral.
Phase A and neutral.
So it is connected between line and neutral. That means you have to take phase voltage, right? If it is connected between line
Yes,
and line,
madam.
then you will take line voltage. Otherwise, you will take phase voltage.
Here they are asking calculate RMS value of supply line currents, madam.
Ma'am,
Both
you
are
are
same,
not
madam.
going to solve this, ma'am. A three-phase four-wire unbalanced load of 120 amps at 0.8 lagging power factor is connected between phase and neutral. So with an input voltage of 415 volts. So it is to be realized as an balanced unity power factor load on three-phase supply system using four-leg PWM based D statcom. Calculate the RMS value of line current. So just a small request to solve this problem on three-phase four-wire unbalanced load problem, ma'am.
Ma'am, I get it that you are facing problem with this, but I am not allowed to discuss assignment problems before the submission deadlines. I am strictly asked to solve similar problems but not the assignment problems. And I know that you guys are asking this from the assignment. So I can discuss it in the next class, but I cannot discuss it right now.
Correct, madam.
I have
That is
given all the
phase
I've given all the hint that I could, but I cannot tell you more than that.
No, no, for this four-wire system, where can we find, ma'am, then? Like, I think it is not there in the lecture session video.
No, it is there. That is what I'm trying to tell you. It is there. See,
Uh-huh.
you won't find
Uh,
exact similar problem, but once you understand how he is solving those problems, you will be able to understand. So the problems that he has taken up in the lecture are much more difficult, are 10 times more difficult than what you are given in the assignments. So once you understand those problems, you will be easily able to solve. So first try to understand those problems, and then from there, I am 110% sure you will easily be able to solve.
so you are not going to solve four-wire system
I
problem.
will do that in the next class. But today I can't take that.
So what is the use, ma'am, then?
I
At
can
least
I
with
have
not with the same data, so like you, as you said, no, with the other data you can
see
solve,
I
no?
am not
So not.
prepared. I have to prepare the slides beforehand, right? And I know that you are asking for a assignment problem, so I have told you all the logic. I have just solved a similar problem. That logic you have to use in the other problem as well. And I have told you that phase line, what to do, how to do it. Now you just have to implement it. The similar logic is being applied there.
Uh-huh. Okay. Hmm.
Yeah, different is same as phase current.
Sir, your voice is breaking.
Madam, phase current is same as that phase 4y.
So you are asked to calculate the supply currents, right?
Supply is not even line current, madam. Supply line current,
RMS value of
not
supply line current, ma'am.
So the line current is the same as the line current means the current flowing in the wire, right? It's not
Yeah.
different. And it's a single
Hmm.
phase load. So all the currents are same only, na? Then what is the? I don't understand the issue. So you have a balance. Once you have applied the compensator, your system will become balanced. That means all the source current will become balanced, and their magnitudes will
Hmm.
be equal, right?
Yeah. Yeah. Yes. Yes.
Now,
Huh.
did you get my point?
So now,
okay,
like,
madam.
okay. Huh.
And you're already given current magnitude, you're already given power factor. You know I cos theta is the good current, I sin theta is the bad current. So now the supply will only supply the good current. That means it will only supply the I cos theta component. So just you have to divide the I cos theta in all the three phases. That's it. We have already done similar problem.
Hmm. Hmm.
Okay, guys, then we'll end today's session. All the best for your assignment. And in case you have doubt in this one, I will add this problem to my list and we'll solve in the next class as well.
Ma'am, the problem is actually they have only UPQC is the lecture session we are having, ma'am, for week 4. So D statcom based, I think it is not there.
D-StatCom base is not there means?
Uh, like only unified power quality compensators are given in the
Okay,
lecture.
so in the previous week, you have already in the lectures that are there for this active shunt compensator continued. I think it's
Huh.
lecture number 7 or 8. I forgot, but
Huh.
that in that lecture, sir has solved I think 20 around problems,
Huh.
and it
Okay.
has problems, and they are actually advanced versions of these problems.
Huh. Okay.
You
Hmm.
should
Hmm.
definitely solve those. Otherwise, assignments will be very difficult. If you don't watch the lectures, then it will be very difficult. You have to watch the lectures thoroughly.
Hmm. Okay. Hmm.
Just watch that lecture. In that, sir has taken up a lot of numerical problems, and in that,
Hmm.
if you are facing problem with only three phase four wire, you can solve only those problems.
Hmm.
Okay,
Okay. Hmm. Okay, ma'am.
okay, guys.
Okay, thank you, madam. Thank you,
Okay,
madam.
okay, guys. Have a
Okay,
good
ma'am,
evening.
then this problem solving session, this video will be immediately uploaded, no? So to the
Yeah,
link.
you have my access of the channel, right? You have my access to my YouTube channel, right?
Okay, okay. We'll get subscribed,
Okay,
ma'am.
madam.
Yeah, you the previous link that I have shared, now.
So to the same, you will be
Huh.
uploading this video.
Yes, yes. To the same link, if you go, you will get access to my channel. In that channel, I will upload. So it takes
Okay.
half an hour around. So in half an hour, you will be able to find the lecture.
Okay.
Okay. Okay. Okay, guys.
Okay.
Then okay.
Thank
Bye bye. Have a good night.